All right. So I already gave a presentation yesterday. I'm Martin. I'm with EDA/National Instruments. I'm also with the GNU Radio, an officer. But this is sort of a side project of mine. So this is all my own opinions. I'm not representing anyone else. And I'm going to talk about out of tree module called gr-specest. And I'm also going to talk about spectral estimation. And I'm going to start at the very bottom. Like I'm going to assume absolutely no prior knowledge. What is spectral estimation? And as a matter of fact, like if you ask that question, like you should start with what is estimation and estimation theory. So as almost everyone in this room, I have an engineering degree. And I have to say, like, estimation theory was one of my favorite subjects. But it was like a big thing. I had like 2 semesters just on estimation theory, and then like another semester on the DSB for spectral estimation, and then probably more classes in there. So I can't summarize all of that. But the key thing to take away from estimation theory is like, this is not guesswork. Like there is, you have stochastic inputs, you have unambiguous mathematical derived equations. They produce some output, and that is an estimation. And just to give you a couple of easy examples. So let's say we're measuring a voltage on a noisy, with some noisy equipment, for example. And now we have to state some assumptions. For example, we'll say, okay, my noise is white Gaussian noise, which always makes the math most easy. And now, like, how do I figure, like, every time I measure my voltage, like, it gives me a different value. Like, how do I know what it's supposed to be? And the answer is, well, I just measure multiple times and, you know, take the arithmetic average. And then people will say, oh, Dr. Braun, is that what they give you PhDs for in Germany? And I say, hold on, this might be intuitive and simple, but I had to get to this equation, I had to put in all the correct inputs first. And this is the same is true for estimation. You have to, like, you know, provide the entire chain, because what if my noise is not white Gaussian? Then this no longer holds true. And you can apply this to other things, like something I'm not very good at. Oh, no, I shouldn't say this in public. Well, something where you can also apply this is estimating software projects. And there's actually also like actual science behind that. You might not believe it. So there's like, I picked the model from a book on software estimation theory. And let's say you have one developer and they say, okay, I have 3 tasks. It takes blah, 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 many days. Like there's some uncertainty in there. You actually model that uncertainty in an appropriate stochastic model. And then you say, okay, like I'm 90% confident this will be done within 12.4 days. And then you round it up a little bit to make it look less ridiculous. But this is not guessing. This is still some underlying mathematical model, which I'm not going to explain here for the lack of time. So the point I'm trying to make here is estimation is solidly grounded in math. And the same is true for spectral estimation. So I give you give me noisy inputs, and then I provide some model, and then the output is the spectrum estimate. But what's the spectrum? That's the next question. So if you just put spectrum into Google, like you find, you know, a wide spectrum of pictures. Like there's all sorts of stuff that you can think of when you just, you know, talk of a spectrum. Like, is this a spectrum? Like, is this a spectrum? Like, which one is the spectrum? Like, one of them has to be the spectrum. And that is also not true. Like, you first make a definition of what your spectrum is, and then you derive your estimator based on your noisy inputs. So I'm actually going to give you multiple definitions for what a spectrum might be. And I'm going to start with this here, non-parametric spectral estimation. Some people also call it traditional spectral estimation. This is a long title, but actually you will probably not be surprised to see what's going to come up next. So in this case, I say, okay, I actually want to estimate the power spectrum density. And this is like probably the only equations I have, so like don't worry. If the power spectrum density. The power spectrum density is typically notarized as S of omega, omega being the frequency. And if you integrate over from like omega 0 to omega 1, then that's the power you get in that band. So that's why it's called the power spectrum density. So we have this thing here, x hat, which is a time-limited Fourier transform. I'm being a little bit unscientific here for the sake of time. But it's also, I think, more intuitive that way. So this is not exactly a Fourier transform because I'm only going over a limited amount of time. Then I'm module square, then I have the expected value of that, and then I have to go t equals up to infinity. If we look at this here, we actually recognize a whole bunch of things. Before I talk about them, I also want to just mention, for the sake of completeness, that there is an alternative way to derive all of this, where the Power spectrum density is defined as the actual Fourier transform of the autocorrelation function, which in itself is also an expected value of some stochastic process. If you care about this, these are called parallelogram-based methods. I will not talk about them. I will go back to the left-hand side. And just follow this here. X of t is my signal. This here is a time-limited Fourier transform. Let's take that to the discrete time, like a time-limited discrete time Fourier transform. Like we just call that an f of t. So like this entire thing is an f of t. This here is an expected value of something. I already mentioned under certain circumstances, expected values can be easy to calculate by arithmetic averages, which is something we do here. And then this whole t up to infinity thing, we're going to have to approximate somehow. So, sometimes it's okay to be an engineer and just throw like the scientific rigor a little bit overboard for the sake of practicality. And that's what this guy did. His name is Welch, and this is Welch's method. Falls out of that. You've probably all heard of this. I'm going to quickly go through it again. I was sitting in the library. I didn't have like fancy graphic tools, so I actually drew this by hand. So imagine you have a noisy signal. You can see I approximated a sine wave here. You split your signal into segments of time. Here they are. Take f of t's of that, and then the module squared of that. You get something like this. There's still plenty of noise here. And then you take as many of those as you like, average them, and then this would be your output. And if you go back to my definition, you can find all the things that I mentioned in there earlier. So segmenting in time, so we can do f of t's. That's our time-limited Fourier transform. The module squared was actually in the definition of the power spectrum density, so I'm not even approximating anything here. And then the more of these I take, the more I approximate t towards infinity. So there you go. And you can even do this in real time by saying, okay, I'm just going to limit this to, say, I don't know, like 32 averages. And then I'm going to sort of always feed in a new f of t, drop the oldest one, and that's how I can like do sort of a time, sort of a continuous update of my spectral estimates. So that's a way of doing it, of doing spectral estimation. And I was saying this is actually about gr-specest. So you can find this in GNU Radio. Looks like this here. So what do we have? We have this block called Welch spectrum estimator, and you put in a bunch of parameters. And you can see the parameters here. Overlap is how much you actually want to overlap the segments. But more importantly, you have an f of t size, which I have as a variable here set to 1024. How many of those I want to average, and a window function, which I will talk about in a bit. I instantiated 4 of these just to give different results, and I hope this works. Oh, thank God. Here's 4 different results. I don't know if you see this jumping thing here. I wasn't quite sure why that comes from. I think it's actually the GUI that does that. It's not supposed to be part of the estimation. What I input here was just 2 unrelated signals. One of them is a sinusoid, and one of them is a GMSK signal. And I just varied the parameters. You can see like here, I have a smaller f of t size, so it's a little bit more coarse. And there's like various other parameters that we can change here to get different types of estimates. I'll go into those in a little bit. The point is these are all valid spectral estimates. They're all different because they all serve a different purpose, and they all use the same algorithm with different parameters. So why is it called non-parametric if I have parameters? The parameters are not about the algorithm, but about the spectrum. So the spectrum does not have parameters, which means I can feed any type of signal in here, and it'll always give me a useful output. Okay, so this is my intro to spectrum estimation. There are plenty of nuances here. And a little thing that I want to throw out to you is if you want to look at one of these estimates, we actually have something in GNU Radio called the QD frequency sink. What is that? I actually compare those here. So Welch spectrum estimator versus the QD GUI frequency sink in this case. First thing you will notice is that this guy is sort of a like one-stop shop for spectral estimation. This actually just does the math and output stuff, and then I have to plot it myself. So that's the first difference. If I run it, first of all, like the QD GUI frequency sink doesn't have this bouncy bug, so that's good. But other than that, depending on the parameters you choose, they actually look very similar. So why should I use one over the other? And the answer is it doesn't really matter as long as you know what you're doing. So the QD GUI frequency sink has a couple of differences. It will drop a whole bunch of samples, which means it's technically not quite as accurate. But the only purpose of this sink is for you to look at it. So it doesn't have to be perfect because your human eye can't track the spectrum anyway that well. And the other thing it does, it uses a single pole IIR instead of a true moving average filter, which is simply more efficient, and which is also fine. So we just basically drop some of the scientific rigor of Welch's algorithm, which we don't need for performance sake. If you were to do post-processing of the signal, where you actually need like every sample or every bin of the output to be exactly as you expected from your equation, then you would use this. That's pretty much it. Oh, that was my demo. However, learning how to read these outputs is not as simple as it looks like. Like, I mean, sure, you can put it all on the frequency thing and say, here's energy, here's no energy, that's it. But like, you can actually like change the parameters in a way that'll give you subtle, different results. So I'm going to run another demo here. And this is, I hope they all fit. So actually, no, sorry, I want to show the flow graph before I show the results. So what am I actually doing here? I'm adding some noise just so I have a noise background. Other than that, I'm going to put in 2 sine waves with the same exact amplitude. And I'm going to plot the result 4 times in 2 different windows. Keep in mind, I'm putting in the same signal twice, okay? Plus noise. Whoops, where's my radio? Oh, here we are. Okay. So I put in I put in 2 different estimates in the top in blue and in red, 2 different estimates in the bottom in blue and in red. I couldn't put them in the same window because they're using different FFT sizes, which is already the first thing. But let's ignore this guy here, the blue one. Just look at the red one. It looks kind of nice. We have 2 tones, so at first glance this is what we expect. Actually, here's a question. Like, what is like I didn't tell you what noise I put in here. What is the signal to noise ratio of this of this tone here? What do you think? Just shout out a number and I'll. Sorry? 50. There you go. Great number. Why not? Because here we have 20. Here we have minus 30. Whatever you would have said, I would have said the answer is wrong. Because the correct answer to the question is, what is your definition of the signal to noise ratio? Because I said I put in the exact same signal twice. This here is 50. Here, if you go by your logic, it's 40. And here, it's actually, you have to zoom in to see that. But this guy is also a little bit lower than that guy. So this would be 50, and this would be like 47 or something. Doesn't really make sense, okay? Like, how can the signal to noise ratio be different? And that's because the parameters of my spectral estimation, or my estimator, actually matter for this case. So what's going on here? Okay, who's paying attention? Why is the signal to noise ratio higher in the top picture versus the bottom picture? Thank you, Tom. The FFT size is different. I said that at the beginning. And why does the FFT size matter? Well, there's different ways to think about it, like depending how you want to visualize it. So the FFT filter is kind of a match filter for sinusoids. So you integrate over a longer period. Thus, at the top, you just add up more stuff. You could also think of it differently, that the sine wave will also drop in exactly 1 bin, no matter how many bins I have. But the noise will always spread out over all the bins. So I have more bins in the top, so I have to like divide the energy on more bins so it'll go down a bit. And another way to look at it is like, this here is a pretty sharp line, whereas here it's not. So like, if you think of it like as integrating over the frequency domain, like I'm basically putting some of the energy in this like the width, where here it's like higher, okay? So that's one part of it. Then why is this guy here lower than that guy? Any guesses? You can't. Marcus.
Yeah, I mean, that one doesn't really hit the FFT.
Exactly. So unfortunately, on this resolution, you can't see everything at once. But I actually like deliberately put them like on like bad offsets. So if I move it around, it'll change. And then finally, what is all of this here? Oh, sorry. So I kind of skirted over that at the beginning. But before calculating our FFTs, we can multiply our signal with window functions. And that also matters. So in a window function is basically a time domain function that we apply to our signal first. If we don't apply a window, which we do here, we do not apply a window in this case, you will see these side lobes. And if you think about it, again, like just trying to sort of visualize all of this, like there has to be some energy in this little side lobe that is not here, which means the left-hand tone will be a bit higher than the right-hand tone, which is the case. You can barely make it out. Like the one is a little bit above the line, the other is a little bit below the line. But if you're like trying to sort of measure your hardware to like less than a dB accuracy, you have to think of these things. Which makes you wonder, where's my slides? Which makes you wonder, if I'm really just measuring sinusoids, is this really the best way to go? And turns out there is alternatives to that. For example, when we look at parametric spectral estimation. So let's say I know absolutely sure, for like no doubt about it, that I will only have white noise and sinusoids. There will be nothing else. Then I can have an alternative definition for my spectrum, which is this here. So I just say, okay, I have like, you know, e to the j, blah, blah, blah. That's my sinusoid. I add noise. Then all that I care about is my amplitude, alpha, and my frequency, omega. So my spectrum is a set of alphas and omegas. That's it. It's not like a squiggly line thingy. So there are subspace-based methods called music and esprit, which do exactly that. There's also other methods that have come a bit later, which we do not have in Specest, so I'm not going to talk about them, which are actually effective for this kind of application. So a very similar setup here. I have noise, I have two sine waves, and here's my esprit frequency estimator. It has some parameters, which I will go into in a sec. I'm going to hit run, and this is my output. And so I have two frequencies going in, 0.1 and 0.2 normalized. And I have two outputs, 0.1 and 0.2. This is kind of unexciting. Like if you look at it, you feel like, well, it's just boring. Those are just numbers. But that's exactly what you wanted. Like well, my model of the spectrum was not like a plot of, you know, x, y. It was a set of numbers. So here's your set of numbers. So this is actually a legitimate frequency estimator. Maybe it's just not what you might think of when you do that. However, if you do like plots, there is also something called a pseudo-spectrum that you can also derive from here. I only have one tone in this example, and this is what it looks like. So this is not exactly the same as the output of the Welch. And you can see like we have like this smooth line. So obviously something is different. This is also another way of visualizing a spectrum. I don't actually know of any practical applications of doing this, but it helps when you sort of learn about the algorithms. Does anyone know a practical application of like plotting a pseudo-spectrum in esprit? Because I only encountered it in classrooms.
I mean, when you're at T too long, like you need to estimate a very short period of time. Then your number of samples limits the length of your T, right? Mm-hmm. That's limiting the number of events you get.
Oh, okay, excellent. So that's a really good point on why these methods are useful. You need very small number of samples to calculate these spectra. I was like specifically asking why would you plot that, because like computers like take the numbers as an input. Okay. Of course, Marcus, this is a great answer now. Derailed my train of thought a little bit. I need to peek on my next slide. Oh yeah, okay. So I don't have time to go into math of esprit music. If you know linear algebra well, it's actually not that difficult. And if you don't, then it is difficult. So I had to just like opt out of explaining how these work. One thing that we need to know about though is we actually use a so-called covariance matrix as an input to our frequency estimator, and that covariance matrix itself needs to be estimated. So I'm just going to quickly show the parameters of this block. You have to tell it the number of sinusoids that you expect. That is, there are ways of not doing that, but like in this particular case, you have to know that. And then you will also give it two parameters for the actual calculation or estimation of the covariance matrix, which is its dimension, and the dimension should be bigger than the number of sinusoids, and also like how many samples you want to input to that. So you can increase the number of samples that you use to estimate your covariance matrix, but then you will need more samples eventually. give up one of the advantages of this particular algorithm. Okay, so we changed our sort of thought pattern. Said, okay, like I'm going to sort of say my spectrum is a bunch of sinusoids and noise. That's it. Is there anything else we can do? Yes. There is a completely, like similar but like different way of thinking about it, which is something like this. Let's say the signal that I'm estimating is actually modeled as like some noise, which is then going through a filter. And then we observe the output here. And now what we want to do is not look at the cumulative signal at the end, but we want to back calculate what that filter was that originally went into that. And that is also a method of spectral estimation. I hope I can visualize this well enough for you guys. So here's a flow graph. So I'm literally producing noise. I'm sending it through a filter. It's an IIR filter in this case, so it's an autoregressive model. And I will show you the actual spectrum, the output of this guy. But also, I'm going to use this guy, which is the Berg spectrum estimator, Berg's method of spectral estimation. And this here, I will give a little bit of a clue what's going on by telling it like the model order. I'm going to say, like, you're supposed to try and figure out what this filter was, and its model order, like the number of coefficients in its polynomial, does not exceed 6. That's it. You go figure it out. And then this here will produce a pseudo-spectrum of its own. Okay, let's run this. So, what do we see here? In red, we see the shape of the actual filter. And in blue, we see the output of the Welch estimator. So you can see it approximates like the filter, but we have those noise squiggles in there. And I said earlier, we don't actually want those. Like, we don't care about that. Like, they're just exciting the filter. But like that's actually not what we wanted. So instead, we use Berg's method. And Berg's method, we've told you are supposed to figure out which filter was the input to this signal. And I did get the scaling wrong, and I couldn't quite fix it in time for this talk. But other than the bouncy bug, which I think is not part of the algorithm, you can see that the difference between this blue line and this red line is, it's much better than at the top, because I actually get a pretty good idea of what the original coefficients were that went into that. Okay, so I've been blazing through, like I said, like 3 semesters at least of electrical engineering stuff, just to give you an overview of spectral estimation. But I did want to talk about this particular out-of-tree module a little bit, because how did it come about? And it was actually published 10 years ago by a bunch of people, including myself, at the CEL. Like, that's the Communications Engineering Lab at the KIT in Germany. It's a university in Germany. And a friend of mine, Jens Elsner, who some of you might know, and we were faced with an interesting problem, because we were switching to the bachelor master educational system, which you always had, but we only acquired in, I don't know, 2000 something. And the particular problem we needed to solve was that we were getting students that were undergraduate, students, and within our curriculum they were supposed to do a project at the end of their degree, like their bachelor's degree, but they only had like 2.5 semesters worth of classes. So we're like, we don't actually have any experience dealing with that. And it had to solve everything, of course. Like, so they needed to be theoretically challenged in order to go into an academic career, like a master's or a PhD degree. They needed to get some practical experience, because they could also leave the university and go work for a company, and then we wouldn't want to be embarrassed by having produced subpar students. And it just should be fun and cool. So we were, for some reason, we were like doing spectral estimation research anyway. So we thought, you know what? We're just going to let them implement every single spectral estimation algorithm there is. And this turned out to be a great idea. So for so many reasons. So first of all, it ticked all of those boxes. This was like not too difficult, but it had like everything in there. It exposed people to not just like textbooks with a lot of math, but also to like the open source community, and like having to show your own code and like air your dirty laundry and push it out in public. And so we did. We put it out on the mailing list, and this was like long before GRCon. So I didn't know any one of these people in person. And then, we got a lot of encouragement from Tom Rondo, for example, and Matt Edis. They were like, oh, this is great. Like, you should do more of that. So we went into this feedback loop of like, we were like, oh, this is like people are interested, and you know, we kept publishing more and more of these spectral estimation algorithms. So we implemented all of these here over the years. I didn't talk about all of them in particular. I left out cyclostationary processing. There is a very well-known algorithm called the FFT accumulation method, which was also implemented. We also added some tools which were just not available in like upstream GNU Radio. Nothing fancy, just like something you need to calculate these various algorithms. And the cool thing about this is still running code. Like you can see, like I'm running it on 3.8 right now. So we started it 10 years ago. It's still available, still works, and I think that's pretty impressive. I'm just really happy that we managed to do that. So what did we got out of gr-specest other than spectral estimation algorithms? So a couple of cool little fun facts here. So there was a group of students, and Marcus was actually one of them, who implemented the music and esprit algorithms. And they also benchmarked various linear algebra libraries. And I don't think the results are still accurate, so I don't want to like quote those. But at the time, it turned out just running native Fortran was the fastest. So guess what? We had Fortran. This is like, I made this screenshot like, I'm sorry?
That was most fault.
It was Mo's fault, okay. Hey, Moritz. But we have running Fortran code. It still works. So we have Fortran code in GNU Radio. So I think that's pretty nice. But it also like led to so many other things. So we published more and more out of tree modules. We got sick of doing that by hand. We created module. Like you might have used gr-module in the past. That sort of, it wasn't exactly born out of gr-specest, but it was like one of the seeds that went into that. And there's another thing that we learned, which was a sort of business sense here. There's a lot of anxiety about publishing stuff that students do. And I'm not quite sure why. Because there's so many students, you can't capitalize on every single line of code that students write. You know, you can't spin every student's bachelor's project into a startup. We actually got a lot out of doing this because we got so much, notoriety, like PR out of this. So, students wanted to join our group because they saw that you could do open source stuff while not sacrificing. This was not an impediment to your academic career. This was actually like part of it. And we went to GRCon and. I showed up at first GRCon, like everyone knew who I was, like because like stuff like this, and I was like, whoa, this is pretty cool. And so and it made us a little more business savvy in a way. That way, like if you're not open sourcing code, but you're also not selling it, then you've basically lost not necessarily money, but maybe some kind of currency that it could be reputation or something. So it opened our eyes to that kind of thinking as well. All right, I know I blazed through like a million things at once, and I hope this wasn't too fast, and also try to make up a little time here. But I think I finished on time. Excellent.
All right.
All right, thank you very much.